All right, so imagine like building something as big and complex as Yahoo's web crawler, right? You've got billions of web pages, constant flow of data servers crashing left and right.
Oh, yeah.
It's like a logistical nightmare.
Yeah, it's a fascinating challenge, though, and that's where ZooKeeper comes in.
Okay, so how does it help with all of that?
Well, think of it like a conductor, leading a massive orchestra.
Okay, I like that.
Yeah, so it's like making sure every instrument plays its part, at the right time.
So bringing order to that chaos of all those distributed systems?
Exactly.
But like, how does it actually do that?
It's more like a central nervous system for these applications. It manages, that critical metadata,
Oh,
like
okay.
the instructions and signals that keep everything running smoothly.
So it's not a database then?
They're not like a typical database.
Yeah.
No, it's not about storing, massive amounts of user data or anything like that.
Gotcha.
It's more about coordinating those processes.
Yeah. Yeah.
Figuring out which server's a leader or what the latest configuration settings are.
Okay, so it's making sure everyone has the right sheet music, so to speak.
Precisely. And to do that, it uses a structure that may be pretty familiar.
Okay.
The hierarchical file system.
Oh, interesting. So directories and files instead of like rows and columns.
Yes, exactly. So ZooKeeper uses these things called zodes as its basic unit of data, and it organizes them in a tree-like structure.
Okay.
Like how you'd organize files on your computer,
Yeah.
And so a service like Yahoo's message broker can use this structure to organize things like topics and server status and other critical information.
Gotcha. So it's an organized system for this metadata, but how does that actually, coordinate everything? What keeps it from becoming like a total free-for-all?
That's a great question. And one of ZooKeeper's coolest innovations is this thing called wait-free coordination.
Okay, wait, free coordination, what is that?
So in lots of systems, if you have one slow process, it can hold up the entire operation.
Oh yeah, like a traffic jam.
Yeah,
It's
exactly.
just one car holding everything up. Okay, so how does ZooKeeper prevent those digital traffic jams?
Well, its API is designed around these wait-free data objects, so the system doesn't get bogged down by those slowpokes.
Oh, okay.
So instead of relying on these blocking locks, where everyone has to wait for a single process to finish, ZooKeeper uses a more asynchronous approach.
Okay, so multiple lanes on the highway.
Precisely.
Letting the fast cars get by.
Exactly. And this design choice leads to some really significant performance benefits compared to systems like Chubby, which rely on those blocking locks.
Okay, so speed is important, but how about making sure things happen in the right order?
Right.
I mean, with thousands of operations happening all at once, wouldn't that just be a recipe for disaster?
Absolutely. And that's where ZooKeeper's ordering guarantees come in.
Oh, okay.
So every request that comes from a client is executed in the order it was sent. This is called FIFO, or first in, first out.
Okay, so it's like a very well-organized line. Everyone gets served in the order they arrived. But why is that order so important in a system like Yahoo's message broker?
Well, imagine if messages were delivered out of order, right? It could disrupt the entire flow of information.
Yeah.
It could lead to all sorts of problems, incorrect computations, maybe even system failures.
Right.
Maintaining that order is super important for consistency and reliability.
That makes sense, but how do clients actually know when something changes in the system? Are they constantly checking back with ZooKeeper? Like refreshing a web page every few seconds?
That would be incredibly inefficient, especially in a system designed for high performance. So instead, ZooKeeper uses this clever mechanism called watches.
Oh, okay, watches.
Yeah, so instead of constantly polling, ZooKeeper clients can set these watches on specific nodes, and these watches act like triggers.
Okay.
So if the data in that node changes, the client gets a notification.
Oh, so it's like subscribing to an alert system.
Exactly. So
Uh-huh.
clients can react to changes in real time without constantly bombarding the system with requests.
So that's much more efficient.
Much more. And this is super crucial for maintaining both performance and scalability.
So we've talked about how ZooKeeper provides a structured way to store metadata, and it makes sure that coordination is efficient and wait-free. And it guarantees the order of operations and even notifies clients about changes. So it sounds like a really solid foundation.
It is.
But what can you actually build with all of this? What are the practical implications?
That's where things get really interesting, because ZooKeeper is like this set of building blocks for creating more sophisticated coordination tools.
Okay.
It's like Lego bricks for distributed systems.
Ooh, I like that analogy. Okay, so what kinds of structures can we build with these coordination Legos?
Well, you can build things like simple locks to control access to shared resources.
Okay.
So think of it like a one-lane bridge. Only one process can cross at a time.
Yeah.
And ZooKeeper lets you build these locks using its basic API.
Okay, that makes sense. But what about more complicated scenarios, like where you have multiple readers but only one writer allowed at a time?
ZooKeeper can handle that too.
Okay.
You can build these things called read-write locks.
Okay.
So multiple processes can read data simultaneously,
Mm-hmm.
but only one can modify it at any given time.
Okay, I see how that would be useful.
Yeah.
But what about situations where you need processes to start and finish a task all at the same time? Like a synchronized dance move.
That's where the concept of a double barrier comes in.
The double barrier. Okay.
So ZooKeeper lets you create these barriers, and they act as synchronization points.
Okay.
So all the participating processes have to be ready before they start,
Mm-hmm.
and they all have to finish before they move on to the next step.
So it's like a starting line and a finish line.
Exactly.
Okay.
Everyone moves in perfect harmony.
I like it.
And what's even cooler is how ZooKeeper uses these things called ephemerals nodes.
Okay, ephemerals nodes.
Yeah, so these are temporary nodes that only exist as long as the client session is active.
Okay.
So if a process crashes or disconnects, its ephemerals node just vanishes.
So it's like a heartbeat monitor.
Exactly. If the heartbeat stops, something's wrong.
Yeah. Okay, that's clever.
And this is just scratching the surface of what ZooKeeper can do. It's a really versatile and powerful tool for coordinating all those complex distributed systems.
Yeah, it seems like it. Okay, so it really seems like it can do a lot. But what about reliability? What happens if a ZooKeeper server crashes?
Well, that's a good point.
Yeah.
We are talking about systems like Yahoo's web crawler where downtime is, just not an option.
Right.
But ZooKeeper is designed with this, fault tolerance in mind.
Okay.
So it doesn't rely on a single point of failure.
Okay.
Instead, it replicates its data across multiple servers. This is called an ensemble.
So it's like having multiple backups then.
Exactly. So if one server goes down, the others can pick up the slack and keep things running.
Makes sense. And how do they decide what to do if, one of them crashes?
Well, ZooKeeper uses a majority quorum, so it can tolerate, the failure of a minority of servers without skipping a beat.
Okay, so even if a few servers go down, the system keeps chugging along.
Exactly.
That's impressive. Okay, so it's designed to, handle failures gracefully, but I'm curious, what happens when a server does crash? How does it actually recover?
Good question. So ZooKeeper uses this clever combination of snapshots and a write-ahead log.
Snapshots and a write-ahead log. Okay.
So imagine taking periodic backups of your computer, capturing its state at a specific moment.
Mm-hmm.
That's basically what the snapshots are. They capture the entire data tree without, interrupting the service.
Oh, so it's like a restore point then.
Exactly. It lets the system go back to a previous state if something goes wrong, but instead of backing up the whole system every time, which would be really resource intensive.
Yeah.
ZooKeeper keeps a log of all the changes made since that last snapshot.
Oh, okay.
So this write-ahead log is like a journal. It records all the updates.
I see. So if a server crashes, it can restore from that latest snapshot and then replay all those changes from the log.
Exactly. It's like fast-forwarding through that journal to catch up.
Okay. That's really clever. So it prioritizes speed and efficiency even during the recovery process.
Yes, and they call this a fuzzy snapshot
Yeah.
because it doesn't require the system to freeze while the snapshot is being taken.
Oh, okay. So it's like a quick snapshot on the fly.
Exactly.
Gotcha. But we've been talking a lot about servers. So how do the clients actually interact with, this ensemble of servers?
Well, each client connects to one server at a time.
Okay.
And remember those fast read requests we were talking about?
Yeah.
Those are actually handled locally by that server that the client is connected to.
Oh, so there's no need to involve the entire ensemble for reads.
Right. But for write requests, things are a bit different.
Okay, how so?
Well, those need to be coordinated across the whole ensemble to make sure everything is consistent and to avoid any conflicts.
Right.
So the server that gets the write request forwards it to a special server called the leader.
So there's a leader. Okay.
Yeah, so the leader acts like the central coordinator for all those write operations.
Makes sense.
So the leader processes that write request, and then it uses this atomic broadcast protocol called ZAB to distribute the change to all the other servers in the ensemble.
ZAB. Okay, so that's how they all stay in sync.
Exactly. It's like a really synchronized relay race.
Gotcha. And this ZAB protocol, what's so special about it?
Well, it's designed for really high throughput and strict ordering guarantees.
Okay.
So it can handle, thousands of requests in different stages of processing, and it makes sure that all those servers agree on the order of operations.
So it's like a high-speed messaging system, but with extra reliability and coordination.
Exactly.
Okay, that makes sense. But what happens if, a client crashes or loses its connection?
Well, that's a good question.
Right, because it would be bad if that caused problems for the whole system.
Yeah, it would. So To handle that, ZooKeeper uses these timeouts to detect client session failures.
Okay, so if a client stops responding for a certain amount of time.
Yeah, then the system knows something's wrong.
It's like that heartbeat monitor again.
Exactly. And if a client can't connect to its current server, maybe because of a network issue, it can switch to another server in the ensemble without losing its session.
Oh, that's nice. So it's like seamless.
It's all about ensuring that availability and resilience.
Yeah, okay. So ZooKeeper seems to have an answer for pretty much every challenge, a distributed system might face. But does it actually perform well in real-world scenarios? Are all these mechanisms as fast and efficient as they sound?
Well, that's the real test,
Yeah.
right? And the researchers behind ZooKeeper, they did some really rigorous testing to see how it performed under pressure.
Okay.
And they found that it can handle, an incredible volume of transactions per second, especially for those read-heavy workloads that we were talking about.
So it can handle a lot of traffic.
It can. And they simulated scenarios with hundreds of clients, all sending requests at the same time. And ZooKeeper handled it all with remarkable efficiency.
That's impressive.
Yeah, it really is a testament to the powers of good design and, a deep understanding of those challenges of distributed computing.
Okay, so it handles failures, it recovers quickly, and it performs well under pressure. But before we move on, I want to go back to those real-world examples we were discussing earlier.
Yeah, let's do that. Let's revisit those use cases.
All right, so the Yahoo fetching service, again, it crawls billions of web pages, but how does ZooKeeper help manage that massive task?
Well, remember how we talked about ZooKeeper managing configuration metadata?
Yeah.
That's really where it shines in the fetching service. It acts like, a central control panel, making sure that all those crawlers operating in parallel are using the latest configuration settings.
Okay, so everyone's playing from the same sheet music.
Exactly. And make sure that all those crawlers have the same information about which websites to crawl and how often to crawl them and all those important parameters.
Yeah, you wouldn't want them getting confused and bumping into each other.
Exactly. And the research paper also talked about the fetching service having a high read-to-write ratio.
Right. Can you talk about why that's important for ZooKeeper?
Yeah. So, as we've been saying, the fetching service does a lot more reading than writing.
Right.
It constantly needs to access those configuration details and check on the status of the other crawlers and get information about, the websites to crawl.
So it's a very read-intensive workload.
Exactly. And that really plays to ZooKeeper's strengths because those read requests are handled locally.
Right.
So the fetching service can get the information it needs super quickly.
So it's a good match for ZooKeeper then.
It is a very good match. And what about the Yahoo message broker, that messaging superhighway we talked about?
Right. How does ZooKeeper help manage that?
ZooKeeper's got a big role to play there too.
Okay.
It helps manage that, complex topic structure, so it ensures those messages get routed to the right subscribers.
So it's like an air traffic controller then.
Exactly. Directing those claims to their designated gates.
Makes sense. So it's not just storing data, it's also, directing the flow of information.
Exactly. It's about ensuring those, millions of messages are delivered to the right places quickly and reliably. And ZooKeeper does all of this behind the scenes. Users sending and receiving messages, they don't even have to think about it.
Okay, so it's managing configuration, it's routing messages. What else is it doing in this message broker world?
Well, it also handles those server failures that we talked about,
Right.
Remember those ephemeral nodes that disappear when a server crashes?
Yeah.
Well, the message broker uses those nodes to represent the live servers in the system.
Ah, so if a server goes down, its node disappears, and then ZooKeeper knows to, trigger that failover process.
Exactly. It's like a built-in alarm system.
I see.
So Message Broker can seamlessly shift that workload to the remaining servers, and there's very little disruption to the messaging service.
So it's not just about coordination, then it's also about resilience and, fault tolerance.
Precisely.
It seems like ZooKeeper is a really versatile tool, for managing the complexities of all of these distributed systems.
It really is. It's amazing how, one system can address so many challenges and do it so elegantly and efficiently.
Okay, so ZooKeeper is clearly, vital for keeping these huge systems running smoothly. But how do they actually measure its performance? Do they do, rigorous testing?
Yeah, absolutely. They weren't just, satisfied with the theory. They wanted to see how it performed under pressure.
Right.
So they ran a bunch of tests to measure its throughput and latency.
Okay, so throughput is all about how much traffic it can handle, right? Like how many transactions per second?
Exactly, like how many cars can fit on the highway.
Right.
And they found that ZooKeeper could handle tens to hundreds of thousands of transactions per second.
Wow.
Especially when it was dealing with, those read-heavy workloads we were talking about.
Yeah. That makes sense. Okay, what about latency then? How quickly does it respond to requests?
Well, that's another area where ZooKeeper shines. They found that read requests were often handled in just a few milliseconds.
So it's fast.
Very fast.
Okay, so it can handle a lot of traffic, and it's fast. That's important.
It's essential. And yeah, a lot of that performance comes from those design choices we were talking about.
Right.
Like the wait-free coordination and that efficient atomic broadcast protocol.
It all adds up.
It does.
You mentioned specific tests. Can you give me some more details about how they actually evaluated ZooKeeper?
Yeah, so one of the key tests was a throughput benchmark where they varied the ratio of read-to-write requests.
Okay.
So they wanted to see how the system performed under different conditions.
So like testing a car on different roads.
Exactly.
City streets versus the highway.
Precisely. And they found that as the percentage of read requests increased, ZooKeeper's throughput just went way up.
Makes sense since it's optimized for read-heavy workloads.
Exactly. Remember, those read requests are handled locally.
Right.
Without that overhead from the atomic broadcast protocol. So it's like taking the express lane.
I like it. Okay, so it aced the throughput test. How did it do with latency?
Well, they ran a benchmark that was specifically modeled after the one used for Chubby.
Oh, yeah.
Another coordination service. It was kind of a head-to-head comparison.
Ooh, a competition.
Yeah, and ZooKeeper actually outperformed Chubby by a lot, especially when it came to those write requests.
So it's faster overall, and it's beating the competition. That's impressive.
Yeah, it is. And again, those design choices we talked about, they probably play a big role in that performance advantage.
It's all about minimizing latency and maximizing throughput.
Exactly.
But one test in particular, the barrier experiment, what was that all about?
Oh, yeah. So remember our discussion about that double barrier?
Mm-hmm, the synchronized dance move?
Exactly. Well, they wanted to see how well ZooKeeper could handle this type of coordination, in a more real-world setting.
Mm-hmm.
So they designed a test where multiple clients had to enter and leave a series of barriers one after another.
So it's like adding more steps to the dance routine.
Exactly. Good analogy.
And how did they measure its performance?
Well, they measured how long it took for all the clients to complete that whole sequence of barriers.
Okay.
Basically, how quickly they could get in sync and then out of sync again.
Gotcha. And what were the results?
ZooKeeper did really, really well. The time increased linearly with the number of barriers.
Okay, so it scales well.
It does. Even as the complexity increased, the system stayed efficient.
So more dancers doesn't slow the routine down.
Not really. And this shows, ZooKeeper's ability to handle this type of synchronized coordination even as the demands increase.
Okay, so it passed that barrier test with flying colors. It really seems like ZooKeeper is, incredibly robust and efficient.
It is.
And it's capable of handling, all these different coordination challenges.
Mm.
It's amazing to see how this concept of, a distributed coordinated system can have such a big impact on the applications we use every day.
Yeah, it really is. It's a great example of how, good design and understanding those distributed computing principles can lead to some really powerful solutions.
Well, this has been a really fascinating deep dive into the world of ZooKeepers.
It has.
We've learned so much about how it works and how it handles failures, and we've seen, how it performs in real-world scenarios.
Absolutely.
So thank you so much for joining me on this journey.
It's been my pleasure.
And for our listeners, we hope you've gained, a new appreciation for the world of distributed coordination and the role that ZooKeeper plays in keeping our digital lives running smoothly.
It's a fascinating topic for sure.
It is so. Until next time, keep exploring, keep learning, and stay coordinated.
That's good advice.